We'll continue where we left off yesterday. We are doing examples of groups, and we saw groups of integers, real and rational numbers under addition, group of non-zero rational and real numbers under multiplication, fourth roots of unity under complex multiplication, 2 by 2 matrices, invertible matrices, and 2 by 2 matrices with determinant 1, which were the general linear group and the special linear group. We'll see some more examples. The set U of n will define this as the set of all positive integers or natural numbers that are less than n and relatively prime to n. For example, for n is equal to 8, U of 8 is 1, 3, 5, 7. For n is equal to 12, U of 12 is 1, 5, 7, 11. Now UFN is a group under multiplication modulo n. For example, under mod 8 multiplication, we can write a table of the group operation. For a group, this is called its Cayley table or the group table. So the rows are indexed by the group elements and the columns are also indexed by the group elements. And an entry in the row indexed with group element I, group element A, and the column indexed by group element B, this entry will be A times B or A star B. Generally, if the operation that we are performing is multiplication, we'll leave out the star and write it as AB. If it is addition, we'll write it as A plus B. So now in this case, 1 times any number will just be 1, will just be the number itself, even in mod 8 multiplication. 3 times 3 is 9, which is 1 in mod 8. 3 times 5 mod 8 is 7. 3 times 7 mod 8 is 5. And this is commutative, so 3 times 5 will be same as 5 times 3. So 5 times 3 is 7, and 7 times 3 is same as 3 times 7, which is 5. 5 times 5 is 25, which is 1 mod 8. 5 times 7 is 35, which is 3 mod 8. 7 times 5 is 5 times 7, so this is also 3. And 7 times 7 is 49, which is 1 mod 8. So you can see that uh, for any A and B in U of 8, A times B is an element in U of 8. So it is closed. And from the table, you can see that each element has an inverse because 1 occurs in each row. So 1 times 1 is 1. So 1 is its own inverse. Similarly, 3 times 3 is 3. Of course, 1 is the identity element in this group. 5 times 5 is 1, so 5 is its own inverse. And 7 times 7 is 1, so 7 is the inverse of 7. So this will be a group for every n. Remember, this is not the same as Zn. Zn is the set of all integers less than or equal to n minus 1. That includes integers which are not relatively prime to n also. Un is, out of all these, you take out 0 and you take only those integers which are relatively prime to n. The reason you are taking only those integers which are relatively prime to n is because a number a which is less than n has a multiplicative inverse modulo n if and only if a and n are relatively prime. I'll leave this as an exercise. I won't prove this. But you can prove that only elements which are relatively prime to n have multiplicative inverse in Zn. So similar to the other groups that we had, for example, the set of rationals under multiplication, we made that a group by discarding 0 because 0 did not have an inverse. And the set of all 2 by 2 matrices with real entries, again, we discarded all the entries with 0 determinant. We only took invertible matrices. We discarded all the non-invertible elements. And that turned out to be a group under matrix multiplication. So similarly here, Zn, which is 0, 1, 2, 3 up to n minus 1, it is a group under addition mod n always, but under multiplication modulo n, it might not have, all the elements might not have a multiplicative inverse. So we remove all the elements that don't have a multiplicative inverse. And that gives you the uh, group U of n. So an element in a group which has an inverse, it's called a unit. So that's the reason why this group is called U of n. You're taking only the units, that is the elements that have inverses from Zn. So for the next example, this is a non-example. So take the set Z4, which is 0, 1, 2, 3. This is not a group under multiplication modulo 4. This is why is this the case? Yes, there is no inverse for 0. 0 times nothing will give you 1. 0 times anything is 0 itself. So you can't get a 1, which is the identity element for multiplication. And what about if we take away 0, then what? Yeah, so 0 has no inverse. 2 also have no inverse. So this is not a group. In all these, anyway, if you take 0, then you won't have a multiplicative inverse in modulo n for any n. But what about ZP where P is a prime? That is the set. Okay, I'll write it as ZP star. Or we'll simply write it as ZP. And if we will just know by context whether 0 is included or not. So if it's multiplication, we will just exclude 0. So this will be 1, 2, 3 up to P minus 1. No, one inverse is 1 itself. Yes, both 1 and P minus 1 are inverses of themselves. Yeah. Yes. We can't really say that 2 and p minus 2, 3 and p minus 3 are will go to 1, but there will be some element uh, that is less than p, which will such that it is the inverse of 2. Again, this comes from this exercise. For any number less than n, it has a multiplicative inverse if and only if that number and n are relatively prime. So here p is a prime number. So for all numbers less than p, they are relatively prime to p. Two numbers are relatively prime if they do not have any common factors other than 1, right? So a prime number does not have is not divisible by any number less than that prime number itself, just by definition. So all numbers less than p and greater than or equal to 1 are relatively prime to p. Then if you show this, if you uh, do this exercise, that means all those numbers have multiplicative inverses. So ZP where P is a prime is a group under mod P modulo P multiplication. Then the set of complex numbers under addition is a group. Identity is 0. Inverse of A plus IB is minus A minus IB. The set of complex numbers other than 0 is a group under complex number multiplication. The identity element is 1. Of course, 0 is a complex number because you can write it as 0 plus 0 I. 1 you can write it as 1 plus 0 I. And the inverse of A plus IB is 1 over A plus IB. And since 0 is excluded, 1 over A plus IB makes sense. This you can multiply by A minus IB, A minus IB divided by A minus IB, which is 1. So the denominator will be A plus IB into A minus IB. So A plus IB into A minus IB is nothing but A square plus B square. So this is of the form A by A square plus B square plus minus B by A square plus B square into I, which is a complex number. So C star is a group under complex number multiplication. Previously, we had seen an example of the fourth roots of unity, but and that was a group under complex number multiplication, we can generalize that to any n greater than or equal to 1. So for all integers n greater than or equal to 1, the set of complex nth roots of unity, which can be written as cosine of k into 360 degree by n plus I sine of k into 360 degree by n, which can also be written in the form e power I k 360 by n, or k going from 0, 1 to up to n minus 1. This set is a group under complex multiplication. Is this all right? Yeah. So in the complex plane, the roots of unity are all on the unit circle. And if n is 4, then these 4 points will be the fourth roots of unity. So this is 1 comma 0, 0 I, 0 1, minus 1 0, minus 1 minus 1. That is this is the I axis. So this is actually 1 plus 0 I, which is 1. This is 0 plus 1 I, which is I. This is minus 1 plus 0 I, which is minus 1. And this is, sorry, this is 0 and minus 1. So 0 plus minus 1 I, which is minus I. So those are the fourth roots of unity. Um, this is the real axis, this is the imaginary axis. Anyway, 1 comma 0, which is 1, is always nth root of 1, because 1 power n is 1 for any n, any positive integer. So that will be a root. Then, if you want to find the nth roots of unity, you have to take points that are you have to you take the line joining the origin and this 1 comma 0 and rotate it by 360 degree by n. So if I want to find the six roots of unity, you have to rotate that ray by 360 by 6. So that is 60 degrees. So that will be somewhere here. And this point will also be a sixth root of 1. Then again rotate it by another 60 degrees. Then another 60. Then another 60 and another 60. So these will all be the sixth root of unity. So uh, and what happens is this is closed because each of the points is also form e power I k1. Suppose one of the points is e power I k1 360 degree by n. I'll write this 360 as 2 pi e power I 2 pi k1 by n. And you multiply that with e power I k2 into 2 pi by n. You will get e power I into k1 plus k2 2 pi by n. If k1 plus k2 is less than n, then you're okay. It is still within this set. Right. This set is set of all I k 360 by n. K is k takes value from 0 to n minus 1. So the k1 plus k2 is 1 of 0 to n minus 1, then you're fine. Suppose k1 plus k2 is greater than n, then you can divide k1 plus k2 by n and write k1 plus k2 is nq plus r, where r is between n and 0. So it's now e power k1 plus k2 into 2 pi by n is equal to e power I nq plus r 2 pi by n. You can split this and write this as I into n into 2 pi by n times I e power I into, sorry, this is n cube times I into r 2 pi by n. This is nothing but e power I into the n's get cancelled here. So 2 pi into q times e power I into 2 pi r by n, where r is a number between 0 and n minus 1, including 0 and n minus 1. Now there is a property that for multiples of 2 pi e power I into, if theta is a multiple of 2 pi, e power I theta is 1, because this is nothing but cos 2 pi q plus I sin 2 pi q, and cos of a multiple of 2 pi is 1, sine of multiple of 2 pi is 0. So this is nothing but 1. So this e power I into nq plus r into 2 pi by n, which was actually e power I into k1 plus k2 by k2 2 pi by n, is equal to e power I 2 pi r by n, where r is a number between 0 and n. So this is actually within the set. So closure is satisfied. Identity is by taking k is equal to 0, you get e power I 0 into 360 degree by n, which is nothing but e power 0. E power 0 is 1. So 1 is the identity. And what is the inverse of e power I k into 360 by n? But in that form, that would not be an element of the set, right? Because yeah, but we saw that e power I 2 pi q or e power I into n into q into 2 pi by n was 1. So e power I 360 degrees is 1. This can also be written as e power I 360 into n divided by n. So this is actually equal to e power minus I k 360 by n, but you can multiply it with 1. 1 is also equal to e power I 360 into n by n. So this will be e power I into n minus k 360 by n. N minus k is within 0 and n minus 1. If k is within 0 and n minus 1. So if k is greater than or equal to 0, less than or equal to n minus 1, then minus k is less than or equal to 0, greater than or equal to 1 minus n. And n plus minus k, which is n minus k, is less than or equal to n, greater than or equal to 1. So it is an element in the set. So we have inverses also. Is that okay? Okay. Now the next example is uh, you have studied vectors, right? Vectors in linear algebra. Yeah. So the set Rn, which is the set of all vectors of the form, you can write it as a1, a2, etc. up to an. That's that a1, a2 are all an are all real numbers. The set of vectors is a group under addition, and addition is defined component wise. So a1, a2, an plus some other vector b1, b2, bn is nothing but a1 plus b1, a2 to a2 plus b2, etc. So this is most of the properties just follow from R. So R was a group under addition. If you define addition to be component wise, then since AI and BI are real numbers and R is a group under, this is addition in R, real numbers. So AI plus BI is also a real number. which means that if vector A, which is A1 to AN, belongs to Rn, and vector B, which is B1 to Bn, belongs to Rn, then each of the AIs and each of the BIs are in R. So each of the AI plus BIs are in R. So this is also a vector with real entries. So closure is fine. Then since it's addition, the identity element is a vector of all zeros. And the inverse of the vector a1, a2, etc. an will simply be minus a1 minus a2, etc. minus an. So in this way, this I have done it for, I've written it for real numbers, but for any group G, you can take a vector of n elements where each of the element is a group element. Then that will also be a group under component-wise addition. So everywhere you can replace R by a group G. And only thing is there, if you replace it by a general group G, minus A1 is simply the additive inverse of A1. This is notation. Minus A means additive inverse of A. Now we had stated 2 by 2 matrices with real entries as an example. And you can extend that similar to how I told here for the set of vectors with real entries. Instead of real entries, you could have had any group entry G. So for matrices, we had 2 by 2 matrices with real entries earlier in the earlier examples, but it holds true for other groups. But here we won't claim that it works for all groups. The set of all 2 by 2 matrices with non-zero determinant with entries from, so earlier we had only with entries from real numbers, but now we can change it to rational, real, complex numbers, or even ZP, where P is a prime. Then this is also a group under matrix multiplication. The only difficulty here is that for Q, R, and C, it is fine. We already know how to find the determinant and the inverse of 2 by 2 matrices and n by n matrices in general. But there is a slight difference when the entries in the matrix are from the group ZP. And the difference is that all the operations are carried out modulo P, and the for Z, if the entries are from ZP, then use mod P arithmetic. to find matrix products, determinants, etc. That's the change. And another change is that earlier we had said for the matrix A, B, C, D, the inverse was 1 over AD minus BC times DA minus B minus C. But for ZP, we don't have a definition of division. So we haven't defined any division operation there. So when it comes to ZP, you simply take, instead of dividing by AD minus BC, you multiply by the inverse of AD minus BC. And this inverse is modulo P inverse. And this minus C and minus B are additive inverses in modulo P addition. So for example, if you take the general linear group, that is a set of all invertible matrices of size 2, so 2 by 2 matrices, with entries from Z7. So Z7 is 0, 1, 2, 3, 4, 5, 6. Consider the matrix 4, 5, 6, 3. Now, the determinant of this matrix 4, 5, 6, 3 is, this is notation for determinant. This is 4 into 3 minus 5 into 6 modulo 7. So this is 12 minus 30 mod 7, which is minus 18 mod 7. And minus 18 mod 7 is, yeah, so it is 3. So that's the determinant. And in mod 7, what is the inverse of 3? Yeah, so it is 5. So now the inverse of the matrix 4, 5, 6, 3 is 5 times 3, 4 minus 5 minus 6 is 5 times minus 5 is 2 minus 6 is 1. So this is 15, 10, 5, 20, but again it's mod 7. So this is 1, 3, 5, and 6. So if you carry out the operations modulo 7 and also instead of dividing by the determinant, you multiply by the inverse of the determinant, then uh, the set of 2 by 2 matrices with entries in ZP is also a group under matrix multiplication. Okay, so I'll make a table of all of most of the examples that we have seen. So we had the integers, rational numbers, real numbers. Operation was addition. The identity was 0. So if k is an element in Z, Q, or R, the inverse was minus k, and the operation is commutative. And we also saw Q plus and R plus. Q star and R star. And the operation was multiplication with identity 1. X is the element, inverse is 1 over x. And that is also an abelian operation. Then we saw the general linear group of 2 by 2 matrices. I'll simply write F to mean any of, so F can be Q, R, C, or ZP. So when it's a prime, I'll write it as ZP. Uh, when I'm not specifying whether it's a prime or not, I'll simply write it as Zn. So again and again, I won't say it is P is a prime because it is very standard notation to use P to mean a prime number. All these under matrix multiplication. The identity is 1001. The element is the form ABCD with AD minus BC is not equal to 0. And the inverse is 1 over AD minus BC times DA minus B minus C. This was an example of a group that is not abelian. Similarly, we have SL of 2 comma F with matrix multiplication. Actually, I can simply copy this. Identity is 1001. The form of the element is ABCD with AD minus BC is equal to 1. So that's the special linear group. Since AD minus BC is 1, the inverse is simply D minus B minus CA. Again, that is also not commutative. Then we saw U of n with multiplication modulo n. Identity was 1. The element was k such that k and n were relatively prime. So GCD of k and n is 1. And inverse, we don't have a particular explicit expression for it, but you can say it is the solution to kx mod n is equal to 1. And this is also abelian. We have Rn, which is a vector space of n vectors of n components. And the operation is component wise addition. Identity is the zero vector. Element is of the form a1, a2, an, where each of the AIs belongs to R. The inverse is minus a1 minus a2, etc. minus an. And this is also abelian. There are some other groups, the dihedral groups, which are the symmetries of regular polygons. Then set of bijections from 1 to 3 and 1 to 3 to 1 to 3. Those I won't write them. These are the most common things that we'll be dealing with for the rest of the course. So the nth roots of unity, all those we'll see them less and less. Okay, that's it for all the examples of groups. So we have seen quite a few examples. Now we'll move on to talking about groups, their properties, and their structure. So we'll move on to elementary properties of groups. So we'll start with very basic properties. So the first thing is when we saw the definition of a group, there the first property was initially the binary operation itself included closures. So it was not stated as a property that a group and its operation must satisfy. The first property was the existence of an identity element. But in that uh, definition, nowhere did we say that there has to be only one identity. You just said there must be one element such that uh, if G is a group element and E is the identity, then G is equal to EG is equal to G. But in fact, it turns out that for a group, the identity is unique. So instead of talking about an identity, you can talk about the identity of a group. So that will state as a theorem the uniqueness of the identity element. So in a group G, there is only one identity element. And the proof for that goes as follows. Suppose we assume the contrary. That is, there is more than one identity. And suppose both E1, or I'll write it as E and E prime, are identities of the group G. Then, since E is an identity element, AE equal to A for all A in G, set A is equal to E prime because that is also a group element. Now E prime E is equal to E prime. Also, E prime is an identity element. So for any A in G, E prime A is equal to A for all A in G by definition. This means if I set A is equal to E here, or if A is confusing, we'll just write it as B everywhere. If B is equal to E, then E prime E is equal to E. From 1 and 2, from equations 1 and equation 2, E prime E is equal to E prime, but E prime E is also equal to E. So E prime is equal to E. So if there is only one identity for in any group, there can't be two distinct identities. Is that clear? Then the next, yes, yeah, yeah. Uh, I just wrote it this way because if sometimes if the material is you have not seen this type of proof that much, then writing it this way explicitly makes it simpler to understand. Otherwise, like you said, we can simply write E prime is equal to E is equal to E prime. The next theorem is about cancellation. So in a group G, the right and left cancellation laws hold. That is, BA is equal to CA implies B equals C, and AB equal to AC implies B equals C. So this we have this in school we do it all the time. We're just dealing with the real numbers or integers. So if we have an equation like 2x is equal to 4, uh, you can write it as 2 times 2, and we cancel out the 2 on both sides. That is called the left cancellation law because you're cancelling out terms on the left on both sides. But that was for integers, real numbers with multiplication operation, and with addition you had 2 plus 3x is 4. Then this you can write it as 2 plus 2, and you can cancel out 2 on both sides. So 3x is equal to 2. So in addition also it holds. That was for integers and real numbers. That was for numbers. But we are saying that it holds in a general group where you don't know what the group G is and you don't know what the operation is. You only know that G has the group properties under that operation. Then the cancellation laws still hold. And the proof is simple. If BA is equal to CA, then you can multiply on both sides. On both sides, you can multiply on the right by A inverse. BA times A inverse is CA times A inverse. And by associativity, BA times A inverse is nothing but B times A inverse. And CA times A inverse is nothing but C times A inverse. But by definition of the inverse, A inverse is equal to the identity element. And by definition of the identity element, B is equal to B and C is equal to C. So BA equals CA implies that B equals C. You just cancel out the A on both sides. Similarly, if AB equals AC, then multiply on the left by A inverse. A inverse AB equals A inverse AC. Then by associative property, A inverse A times B is A inverse A times C. EB equals BC. So B is equal to C. So again, you can cancel identical terms on the left. That's the cancellation law. Then another basic property is the uniqueness of inverses. In the definition, we said that for every element A, there must be another element B, which is the inverse of A, such that AB is equal to BA is equal to the identity element E. But we didn't say that the inverse has to be unique. We just needed each element to have one inverse. We didn't have any problem if there are more inverses. But it turns out that there is only one inverse for each element. So for each element A in a group G, there is a unique element B in G such that AB equals BA equals the identity E. Again, like earlier, we'll assume that this is not true. So suppose this is not true. That is, suppose B and C are both inverses of A. Then, since B and C are inverses of A, AB is equal to E and AC is equal to E. So AB equals AC by the previous theorem, by cancellation. We cancel out the A's and write B is equal to C. So there can only be one inverse. There can't be two distinct inverses. Then another useful thing, a useful fact, I won't really call this a theorem. Let G1 and G2 be two elements of the group G. Suppose G1 times G2 is equal to E. Then G2 times G1 is equal to E. So in general, G1 G2 is not equal to G2 G1 for a group G. So if the group is abelian, then it's true that G1 G2 is equal to G2 G1 for all G1 G2. If the group is not abelian, then it doesn't have to be true. But if G1 G2 is equal to E, then definitely G2 G1 is E. So that G2 is the inverse of G1 and G1 is the inverse of G2. So in the usefulness of this is that to find an inverse, you don't have to check both directions. In the definition, the inverse is defined as that element B such that AB is equal to BA is equal to E. But this makes it so that you only have to check if AB is E or BA is E. If you check that, then automatically the other thing is satisfied. And the proof is as follows. G1, G2 is equal to E implies that you can multiply by G1 inverse on both sides. G1 inverse, G1, G2 equals G1 inverse E, which implies that G1 inverse G1 times you can use associative property. So G1 inverse E. And by definition, G1 inverse G1 is the identity element E. So G2 is equal to G1 inverse. That means that by definition, G2 G1 is E, or you can write multiply. G2 G1 is G1 inverse G1, which is E. So G1 G2 is equal to E will always mean that G2 G1 is also E, and G1 and G2 are the inverses of each other. So those are three basic theorems and one basic fact about groups. There is a unique identity element. Each element has a unique inverse, and you can do left cancellation, right cancellation. Also, to find an inverse, you just need to find an element such that if B is the inverse of A, then if you show BA is E or AB is E, only one of those conditions is sufficient to know that B is the inverse of A. Now we'll move on to some problems. So we'll solve a lot of problems in the beginning, just so that we get used to the concepts. And later on, if we have a lot of time, we'll keep solving lots of problems. But depending on time, we'll cut down on the problem solving. So initially, check whether the following are groups. So the first set is G is the set of integers, and the operation is subtraction. Is this a group? Yes, set of all integers. So, but this would only be true if you have to. That's why it is the definition is precise. So in the definition, we say that A star x is equal to A, but that is not the only condition for it being an identity element, right? X star A should also be A. If if E is an identity element, A star E should be equal to E star A, and that should be equal to A for all A in G. So certainly A star 0 is A minus 0 is A. That is fine. But what about 0 star A? That is 0 minus A, which is minus A, right? It is not equal to A in general. For all elements other than 0, plus A and minus A are different. So 0 cannot be the identity element. So there is no identity element. Yes. So it is not a group. Thus, there is no identity element. In fact, we can also check another property, which is the associativity. Associativity is also violated for subtraction because 5 star 3 star 2 is 5 star 3 minus 2 is 5 star 1, which is 5 minus 1, and this is 4. But 5 star 3 star 2 is, so the bracket means that you have to do the bracket operation first. Is this 5 minus 3 star 2 is 2 star 2, which is 2 minus 2, which is 0. So associative property is also not satisfied by subtraction. So there are, because of both the reasons, I mean one reason would have been satisfied, would have been enough to disqualify that group. So Z is Z is not a group under subtraction. That was the first problem. Check whether the following are groups. We saw Z and subtraction. What about the Z and the operation A star B is defined to be A plus B plus AB, or you can write it as A dot B or AB. We mean A into B. Okay, so this is ordinary multiplication, and this is ordinary integer addition. So would this be a group? First, we have to see closure. If A and B are integers, A star B is A plus B plus AB. Is that an integer? So that is an integer. So it is closed. So it is a binary operation. What about the identity? Let's, yeah. So A star x is A plus x plus AX, that is equal to A. We'll say E if it exists, then E plus AE is equal to 0. Subtracting A on both sides, then E into 1 plus A must be equal to 0. So, yeah, so E equals 0. Now, A times 0 is A plus 0 plus A into 0, which is A plus 0 plus 0 is A. We also have to check 0 times A, but that is again uh, 0 plus A plus 0 into A, which is 0 plus A plus 0. So that is also A. So identity element does exist. 0 is the identity. Okay. Then first let's check the associativity. What is A star B? Then start with C. This is A plus B plus AB. Start with C, which is A plus B plus AB plus C into A plus B plus AB. Right? So you can there's no confusion with how this is done, right? How the operation is applied. Okay, so if we rearrange these terms, we can multiply C and A plus B plus AB, and then we can rearrange these terms to get A plus B plus C plus there'll be AB, then there'll be BC, and then there'll be a CA. There's a CA there plus ABC, AB times C. If we do it the other way, A star B star C, this is nothing but A star B plus C plus BC, which is nothing but A plus B plus C plus BC plus A into B plus C plus BC. Again, if we write it and rearrange the terms, you will get A plus B plus C plus AB plus BC plus CA plus ABC. So associativity is also satisfied. A star B star C is nothing but A star B star C. Only thing we have to check now is the inverse. So suppose A is an integer, A belongs to Z, and B is the inverse of A. B also must be an integer. Yes. Which would imply A plus B plus AB equals 0. Should mean that 1 plus A times B equals minus A. We are solving for B, right? In terms of A. Now, before doing that itself, let's suppose A is equal to minus 1, right? Then minus 1 star B is what? Minus 1 plus B plus minus 1 times B, which is minus 1 plus B minus B, which is nothing but minus 1 plus 0, it is minus 1. That is not equal to 0. So minus 1 does not have an inverse directly, right? So Z is not a group under this operation, right? Z comma star, yeah. So if A is not minus 1, we can divide both sides by 1 plus A. Then B is equal to minus A by 1 plus A. So even if we exclude 1, if Z minus the set 1, set containing 1, that would not be a group. So either way, Z star is not a group. So we had to discard 1, discard minus 1, and also we have to include fractions. So we might check for rational numbers. So if G is the set of rational numbers minus the set containing minus 1, then G star is a group. So the only problem for us was the inverses, and if we make the set into the group of rational numbers, then it has an inverse. Every element has an inverse except minus 1. So if we take away minus 1, it forms a group. The next one is, let G be the set A by B rational numbers such that A comma B are co-prime. That is, you write A by B in the lowest terms. You cancel out the common factors and then write it in the lowest possible terms. So what I mean to say is that 2 by 4 is not in G. You have to write it as half. Half is in G. So you have to take the lowest uh, factor, the rational number in the lowest terms. And 5 divides B. Is this a group? Star is addition. Addition of rational numbers. 5 has to divide the denominator. G set of A by B. Yeah. 5 divides B is the condition. Yeah. Yeah. So closure is not. Another example is simply take 1 by 5 and 4 by 5. That will be 5 by 5. This is 1 by 1. Yeah, since we have to write in the lowest terms. And 5 does not divide 1. So this is not closed. So this is not closed. So not a group. How about instead of taking the condition that 5 divides B, we'll take the set G prime. Again, it's the set of rational numbers in the lowest terms. A, B are co-prime. And 5 does not divide B. And the operation is addition. Now is it a group? So take in general any two elements of the group. Then 5 does not divide B. 5 does not divide D. The sum of the two numbers will be AD plus BC divided by BD. So we had done a lemma in the first class, the Euclid's lemma. For a prime number P, if P divides AB, then P divides A or P divides B. So the contrapositive of that would be if P does not divide A and P does not divide B, then P does not divide AB. And 5 is a prime number. So, like we said, 5 does not divide B and 5 does not divide D. So 5 does not divide BD from here. If 5 does not divide BD, 5 also does not divide any factor of BD. So even if you cancelled some common factors from AD plus BC and BD, like how we did here. When you add 1 by 5 and 2 by 15, then you got 5 by 15, and but you ended up canceling common factors. There were common factors to them. So it became 1 by 3. But even if that happens in this case, it's still 5 still won't divide the denominator. So if 5 does not divide a number, it can't divide any factor of that number. So this is close. What is the identity element? This is addition, right? Yes, rational includes 0. Because you can write 0 as 0 by 1. And one more thing was that they had to be in the lowest term, and that I have written by stating that A and B must be co-prime. 0 and any number are co-prime. Sorry, 0 and 1 is co-prime. 0 and any number is not co-prime. 0 and 1 are co-prime because by this is why we need that definition that I did in the preliminaries, because we can make this precise. So we said that two numbers are co-prime if there exist integers, if their GCD is 1. So and GCD is 1 if their integer exist integers S and T such that AS plus BT was equal to 1. So for 0 and 1, you can write 0 times any number S plus 1 times 1 is 1. So there exists a linear combination of 0 and 1 such that 0s plus AS plus BT is 1. So the GCD of 0 and 1 is 1. And they are relatively prime or co-prime. So 0 by 1 is a member, and 5 does not divide 1. So 0 by 1 is a member of our set. So 0 by 1 belongs to G prime. And this is the identity. The GCD of 0 and any positive number is just the number itself, because all numbers divide 0. Then the inverse is simply inverse of A by B is simply minus A by B. So 5, if 5 does not divide B, then even in minus A by B, the denominator is still B. So 5 does not divide B. So minus A by B will also be a member of G prime. And associativity we simply get from addition in rational numbers. So that property is inherited when you take a subset of the rational numbers. So addition is an associative operation. So G prime is a group under addition. For the next two problems, we'll need some notation. And I'll write down some notation. So for a group element G, let small g be a member of the group, capital G. G power minus 1 is the inverse of G that I have been using already in for multiplication. This is actually just notation. This does not mean that this is equal to 1 divided by G. For complex numbers, real numbers, and rational numbers, G inverse is simply 1 over G. But in general, for a group, for example, for matrix groups, division is not defined. So G inverse is notation for the inverse of G, and for a positive integer n, G power n is G times G times G, this n times. So here there's actually G star G, and since it's a group, star is associative, so we don't have to put brackets here. And if this operation is sometimes it is denoted by multiplication symbol. Even if it is on multiplication, you can definitely simply call it multiplication and denote it by that symbol. And when it is multiplication, we usually ignore this star and write it as this. So this is actually this. So g power n, if n is positive, is just g times z times n times. G power 0 will define that. This is by definition, it is equal to the identity element E. And if n is a negative integer, then g power n is nothing but g inverse power magnitude of n. For example, g power minus 2, if I write this is actually means g inverse power 2. So this is actually g inverse same g inverse. And unlike real numbers, in an abstract group, we do not allow non-integer exponents. So g power half, an expression of this sort, is meaningless. So that is the notation. With this type of notation, usual exponent laws will hold. So with this notation, you can write g power m times g power n is g power m plus n. Why is that? It's because g power n actually means g m times followed by into g n times. So you're actually multiplying by g m plus n times. And g power n is equal to g power mn. Why is that? That is because g power m. So if you take this as some element a, this is a power n, which by definition is a multiplied n times, right? But a is g power m. So g power m multiplied m times. But each of these g power m's is again g multiplied m times. So this was n times, and within one group, this is m times. So it is actually g multiplied mn times. Is that clear? That negative, it's still an integer. This exponent is -2 is still an integer, right? You can have your negative or positive integer exponents, but it can't be a fraction. And so modulus of negative integer is a positive integer, right? So here, when I say g power n is g multiplied n times, g power -2 can't be g multiplied -2 times, right? There's no such thing as carrying an operation out -2 times. No. So what I actually mean is I am carrying out the operation n times the actual absolute value of n times. So okay, by mod I meant the modulus function, absolute value function. Yeah, when n is a negative number. So uh, when n is negative, it's actually uh, multiplying g inverse positive number of times. So this two number twice here. With some other integer n, absolute value of n times. So one thing we have to note is that for groups in general, if it's not an abelian group, AB whole power n is not equal to A power n B power n. That law of exponents is not true. So AB square is equal to AB times AB. Is not equal to A square B square. A square B square is ABB. So here this AB and BA can be different depending on the group. Only if AB equals BA, then these two will be equal. But if they are different, then you will get different elements. And one more thing about this notation is the notation is different if the operation you're doing is you consider it as a multiplication or an addition. So for a multiplicative group, you might write A times B or AB, and the operation is called a multiplication. So note that when I say multiplication, it doesn't have to be multiplication of numbers, right? Even matrices have matrix multiplication. Complex numbers have complex number multiplication. But the notation is same for all of them. If they are matrices I can denote by A capital letters. I can write it as A times B. But what we are doing is actually matrix multiplication here. That is clear from the context. Similarly, for addition, A plus B is the notation. If it's multiplication, the identity element is denoted by either E or 1. So here this 1 does not mean the number 1. 1 means the multiplicative identity. To avoid confusion, many times we will write that as E also. But if I write 1, at least from the context, so you should be able to understand whether it is the number 1 or the identity 1. So you can say that 1001 is the one unity element of matrix multiplication. So you can denote this by 1 because writing 1001 every time is so in matrices we simply call it IE, but in a general group there might not be a standard name for the identity element. We'll simply call not denote it by 1. Similarly, when 0 is the notation for the 0 element, this is the identity. This doesn't mean the number 0. Even if it is not 0, you can still call it the 0 of the group. So there's some slight abuse of notation, you could say. If possible, we'll simply stick to E for the identity in either case. But many places, you should know at least the standard notation. So 0 is used for the additive identity and 1 is used for the multiplicative identity. Then the inverse, you'll write it as A inverse. When it is multiplicative inverse. But the additive inverse is written as minus A. Similarly, other powers also. When I write A power n, this is A into A into A n times is the power of A. Here, the notation is n times A, n A. So this dot is not the group operation. Even if I don't write the dot, this does not mean n into A as the group elements. This is notation to write A plus A plus A n times. So in some groups, for example, the integer groups, NA adding A n times is the same as multiplying n by A, right? But it's not the case for all groups. For other groups, it will just be notation to mean you're adding A n times. And we'll say it's a multiple of A, but actually you're carrying out the group operation on the same element n times. And you might write A B inverse. So instead of division, we don't really have division in all groups, but you can do the product with its inverse. And the analogous quantity would be the difference, A minus B. So depending on the group, the notation will change. That you'll get with practice. Now, one more theorem I want to do is if G is a group and A, comma B are elements of G, then the inverse of AB is what will it be? Yeah. What is it in terms of A inverse and B inverse? What is the relation with that? Yeah. Similar to matrices, it is true for all groups. So the inverse of AB is B inverse A inverse. A proof is that. So what is meant by the inverse of an element? The inverse of element is AB inverse times AB equal to AB times AB inverse equal to E, right? That is what we mean by AB inverse. And previously, I had shown one theorem that if you prove one of these things, then that inverse condition is satisfied for the other thing also. So it is enough to show that AB times B inverse A inverse is equal to E, right? Then one way you can think of this is AB times AB inverse is E and AB times B inverse A inverse is E. So by left cancellation from these two, B inverse A inverse is equal to AB whole inverse. So now AB B inverse A inverse, this you can change the brackets because of associative property. So this is what I have to show. If I show this, then that means AB whole inverse is equal to B inverse A inverse. But that is simple because AB times B inverse A inverse equals A times BB inverse times A inverse, and BB inverse is the identity element. A times the identity element is nothing but A into A inverse. So this is nothing but the identity element. Thus, the inverse of AB is B inverse A inverse. And this property is called the socks shoes property. That is because when you are wearing your socks and shoes, you first put on your socks and then your shoes. But when you want to reverse the process, when you want to take off the socks and shoes, you first take off the shoes and then your socks. So the order is reversed. That's why it's called the sock shoes property. Now, with that notation, we'll solve two more problems. So the first problem is show that For every A in G, there exists a positive integer n such that A power n equal to E if G is a finite group. And G is a finite group. What does that mean? That simply means that G has a finite, so the set G has a finite number of elements. For example, U8 and U11 and Z7. All these are finite groups because they have finite number of elements. Whereas the set of complex numbers, real numbers, integers, they have infinite number of elements, so they are not finite groups, or you can say they are infinite groups. So what this problem is saying is that if a group is finite, then for some integer n, so fix one element a in G. So pick an element first, then for that element there will be some integer n such that a power n is equal to e. And the proof for that is this. Consider e a a square which is a times a cube which is a times a power 4 etc. and so on. Consider all powers of a. Because of closure, by closure a square etc. all belong to G, right? A square is a times a. By closure a times a must be in G. Then a cube is a square times a. By closure that has to be in G. Similarly, a power 4, a power 5, etc. all are elements of G. So for any positive number n, a power n must be in G. But G is a finite group. So what does it mean? This set I have written here, it's a set of infinite elements. But we are saying that there are only finite elements in the group. That means that for some integer, for some integers m and n, a power m must be equal to a power n. Is that all right? At some point it has to repeat. Otherwise, if it does not repeat at all, then it will, if each of the powers are different, then it will be an infinite group, which is not true. We are assumed that it's finite. So, a power m is equal to a power n for some m and m not equal to n. So, two different powers. Then, without loss of generality, we can assume m is greater than n. So, whichever is greater, we'll call that as m. Whichever is smaller, we'll call that as n. Then, a power m is equal to a power n implies that a power m times a power minus n is a power n times a power minus n. So a power minus n is nothing but a inverse n times. So these are positive integers. So it is a inverse inverse n times. So by the law of exponents, this is a power m minus n equal to a power n minus n. This is a power 0, which is the identity. So, and that's it. We have found an integer m minus n since m is greater than n, m minus n is a positive integer. So there exists a positive integer m minus n such that a power m minus n is e. That is what we had said, right? We had to show that for any element a in G, there exists a positive integer n such that a power n is equal to e. Yeah. So uh, here, for example, you can say if a power 5 is equal to a cube, and multiply both sides by a inverse. F that will mean a power 4 is a square. And again multiply by a inverse, that will mean a cube is equal to a. Then again multiply by a inverse, that will mean a square is equal to e. So you can carry out this procedure multiplying both sides by a inverse, the smaller integer number of times, and you will end up with some power of a being equal to e, some positive power. That's what I mean by the previous proof. Could you explain that again? Okay. No, but how will this lead to the identity? Yeah. So we don't already know that some power of A is E. Yeah. Okay. This is not true if G is not finite. This logic only worked because uh, two different powers of A had to be equal. But if it's not finite, for the example, the set of integers, then one is an element of G, but 1 plus 1 plus etc. N times is not equal to 0 for any n. So if you keep adding 1 to itself, you will never get 0. So here the notation was multiplication, so I wrote it as a power n is equal to e. In additive notation, that would be n times a is equal to 0. So it's not true for a group that is not finite. The last problem for today is let G be a finite group. Show that there exists a positive integer n such that a power n equals e for all a in G. So in the earlier problem, we said that first you pick an element A, and regardless of what element you picked, there will be some number n such that a power n is equal to e. But for different element, suppose you pick a different element, then there is a different number. There might be a different number such that b power n, m is equal to e. Here, what we are saying is there is at least one number such that if you raise every element to that any element to that power, then it will be equal to the identity. Yes, yes. So there is one common number such that a power n is equal to e for all elements of the group. Here it said that there is one element n, one number n such that a power n is equal to e, but that n could be different for different elements. The previous problem. Here we are saying that there is one common n such that a power n is e for all the elements. And I can give two such numbers. So one number would be n is equal to the product of n a for all a in G, where n a is a number such that a power n a is equal to e. So since from the previous problem there exists some number for each element a such that a power n is equal to e, and for element a I will call that n a. So and let's say the group is set a1 a2 a up to ar. So this will be product of NAI for each AI in G. And NAI is the number such that AI power NAI is equal to E. Then if you take, let's say, A1 power N, this will be A1 multiplied N times, which is actually NA1 into NA2 into etc. NAR. I defined N to be the product of all these numbers. Then you can write this as, you can group them. NA1 of the A1s, then another group of A1s, and how many such groups will be there? No, each group contains NA1 terms. The total number of terms is NA1 into NA2 into NAR. So the number of groups is NA2 up to NAR, or N by NA1 number of groups. So there are N by NA1 groups, each containing NA1 terms, right? So let's say you have A power 15. Huh? You can write it as A into A, 5 of these groups, right? That's what I am saying. So I have 15 A's. A into A, I have 15 of those. I can group them into groups of 3, and there will be 5 such groups. So here my NA1 is 3 and N is 15. So N divided by NA1 is 15 by 3. That many groups of A's I have, with each group having NA1 number of A's. And this is a valid integer because N is the product of all these NA1, NA2, etc. So N divided by NA1 is also an integer, and it is equal to NA2 times NAR. So N was NA1 into NA2, etc. If you cut away, if you divide by NA1, what you're left with is NA2, NAR, etc. Is that clear? So this is A1 power NA1, right? Into A1 power NA1 into A1 power NA1, N by NA1 time. Each of these groups has NA1 number of terms. But A1 power NA1 was by definition E. NA1 was a number such that A1 power NA1 is equal to E. So this is nothing but E into E into E. What I'm saying is, if G is a group which has, let's say, it has if if there are two elements G, right? Then let it be a finite group. And suppose that a square is equal to e and b cube is equal to e, right? Uh, the previous problem showed that there is at least one number such that a square is equal to e, such that a power n is equal to e. Here n is 2. And for element b, there is some integer such that b power that integer is e. Here I will take assume that b cube is e. Then a power 6 is simply a square cube, which is e cube, which is e. And b power 6 is simply b cube square, which is e square, which is e. So if I take the product of the integers, then if I raise any of the group element to that power, it will be e. This could also have been the LCM of Na1, Na2, etc. Didn't have to be the product. So suppose this was 2 and 4 instead of 2 and 3. So a power 8 is a square power 4, which is e power 4 is e, and b power 8 is b power 4 squared, which is uh, e squared, which is e. But the LCM would also have worked because LCM of 2 and 4 is 4. So a power 4 is a square whole square, which is e squared, which is e, and b power 4 is e. That is given. So the product of those integers or the LCM of those integers, both will work. So that's it for the problem. Here, one thing you have to be careful is this we can write it if it's just one element, right? We are raising only one element to power n. You can write if n is a power mn, you can write the a power m power n. But if you have multiple elements, you can't. Okay, you can still write this as if you have a power m, b power m power n, then you can't write this as a power mn, b power mn. This is equal to a power m, b power m into a power m, b power m, etc. n times. These two might not be equal. Only because we have one single element here, you can write it however you want. That is, A commutes with itself. That's why you can do these manipulations with single element A. Okay, that is all for today's class. Next week, first class, first class will continue with problems. We'll do some more problems based on these basic definitions of groups. And uh, on Thursday and Friday, we'll start with the new topic. All right. Good night. Bye.